Hello, I'm Lubo, and this is my Lab 1 charge tape video lab report. The purpose of this lab is to observe the interaction between two charged pieces of tape, and the results from this lab were that each charged piece of tape in our investigation was found to have 4.375 times 10 to the 10 electrons in deficit, and this equates to each tape having a charge of 7 times 10 to the negative 9 coulombs of positive charge. The physics principles used in this lab are Newton's first law of motion, stating an object will not change its motion unless a resultant force acts on it. Newton's second law of motion, stating force equals mass times acceleration, which will be used to calculate the weight force acting on the upper tape, which we will learn more about later. And Coulomb's law, stating that the electric force between two charged objects is directly proportional to the charges of these objects and inversely proportional to the square of the distance between these interacting charges. A quick run through the experimental procedure. We'll first stick a base tape to a table, then stick another tape on top of the base table and remove it with a quick motion, which induces charge on our upper tape, which we place between the two wooden blocks in the figure on the right. This is tape B. Step 2 is repeated to charge tape A, and then tape A is placed below tape B in order to observe this interaction between the two tapes, and the separation between the two tapes is recorded. The system in this particular experiment is the top tape, and the surroundings is the lower tape and everything else. Initial conditions worth noting is that our upper and lower tapes have a length of 20 centimeters and a width of 2 centimeters each. The linear mass of each tape is 1 gram per meter, and as a result, each tape has a mass of 0.2 grams, and the distance between the wooden blocks in the experiment is 14 centimeters. Here you can observe what the experimental procedure looks like. Some notable experimental assumptions are that the only forces acting on the upper tape rested between the blocks are the tape's weight force and the electrostatic repulsion from the tape below it, and that both tapes are treated as point charges. The separation between the two tapes measured at force equilibrium was found to be 1.5 centimeters. For force balance to occur, the gravitational force needs to equal to the repulsion force from the lower tape. The gravitational force was found to be 0.001962 newtons. This is equated to the equation for the electrostatic repulsion from the lower tape. And with that, we find that both tapes have a charge of 7 times 10 to the negative 9 coulombs. Additional information we were asked to find is the number of electrons on each tape, which was found to be 4.375 times 10 to the 10 electrons per tape. The number of atoms per tape, which was found to be 4 times 10 to the 17 atoms per tape, and the ratio between electrons in the tape and the number of atoms per tape, which was found to be 9.14 times 10 to the 6 atoms for every electron in deficit on the sticky tape. Here you can observe the initial conditions in our glow script code, which is the charge of an electron, the gravitational constant, the length and dimension of each atom, as well as the tape mass and length and width of each tape. The computational code gives us the force of gravity on the upper tape and the electrostatic repulsion force acting on the upper tape. Those two are equated to each other, and this code also gives us the number of electrons in deficit in each tape. This is the visualization we're provided with after we run the code. We can see that the electrostatic repulsion force from the lower tape, which is expressed as the blue sphere, which is the green arrow, is equal to the weight force acting on the upper tape, the orange arrow, as they're of the same length. As a conclusion, we can conclude that the charge induced on each tape through the experimental procedure is positive, and possible sources of error in our investigation are that the tape lengths could have not been measured correctly, error in measurement of the separation due to inability to measure this distance in great precision, and negligence of the reaction forces from the wooden blocks, as well as the effective mass of the tapes being slightly different due to the tapes being stuck at a different distance than the original 20 centimeters between the wooden blocks. For the what if discussion question, if electrons had positive charge and protons negative charge, then our observations from this investigation would not change since the interactions between the like and opposite charges will remain the same. The only difference would come in how we present the accumulation of charge in the tape, as the removal of electrons by the experimental procedure would result in a deficit of positive charge, resulting in each tape being negatively charged. And our final discussion question, why is it important to not handle the charged tapes during the experiment? The reason is that our hands and other objects can serve as media through which charge from the tape can dissipate into its surroundings. As a result, if the tape comes into contact with our hands and other objects, charge from the tape may dissipate, weakening the electric charge on the tapes. As a consequence, the intended interaction between the oppositely charged tapes would be more challenging to observe. In addition, excessive handling and movement of the tapes during the experiment can lead to uneven charge distribution, and as a result, the results of the experiment may be unreliable.